Welcome everybody to our business math course. We are discussing the derivative of exponential functions in the present video. This is Magda Talib Al-Hinai from Sultan Qaboos University and I welcome you all. The current slide, we start our presentation with the derivative of inverse of a function. If we have a function which is differentiable and invertible, then the inverse of this function f minus 1 is also differentiable and will be given by derivative of f minus 1 of x is equal to 1 over f prime of f minus 1 of x. First, let's start with this property of a function and its inverse. The composition of a function and its inverse f of f minus 1 of x is equal to x. Now, if we think of differentiating both sides of this equation with respect to x, what will we get? On the right-hand side, we get a 1. While on the left-hand side, we apply the chain rule. The chain rule is the derivative of a function of a function. So we will have the derivative of the first function with respect to inside multiplied by the derivative of inside with respect to x. So this will be written as the derivative of f with respect to inside times the derivative of inside with respect to x. So from these two equations, we can say that f prime of f minus 1 into d by dx of f minus 1 of x, which is the right-hand side here, is equal to the right-hand side here is equal to 1. And accordingly, we can find d by dx of f minus 1 of x to be equal to 1 over f prime of f minus 1 of x. Now, this is the result we were looking for at the very beginning. Now, if we put y equals f minus 1 of x, then this is equivalent to saying that f of y is equal to x. If we differentiate both sides with respect to y, what will we get? We will get f prime of y is equal to dx by dy. F prime of y is equal to dx by dy. Look at this. Y is equal to f minus 1 of x. Replace it with f minus 1 of x. Let's see. So we will have f prime. Instead of y, we will have f minus 1 of x is equal to dx by dy. Now we have the derivative of this is equal to dy by dx. The right-hand side is differentiated with respect to x. We compare both to one another and take into account this first equation. So from 1, 2, and 3, we come out with the result that dy by dx is equal to 1 over dx by dy. Now, after discussing the derivative of the inverse of a function, we take y equals e power x, which is the inverse of ln function. E and ln are a function and its inverse. So we have y is equal to e power x. This is equivalent to say that x is equal to ln y. Therefore, we have, when we think of differentiating both sides of this relation, we have dx by dy. We differentiate both sides with respect to the variable y. So the left-hand side will be dx by dy. The right-hand side will be 1 over y multiplied by derivative of y with respect to y, which is 1. So we have dx by dy is equal to 1 over y. Now let's see the y itself and we view it as e power x. So we can write that dx by dy is 1 over e power x, replacing y by e power x. More, we have the derivative of e power x. Look at the first equation up here. The derivative of e power x with respect to x. This is what we are searching for. The derivative of e power x with respect to x is equal to the derivative of y with respect to x. So here we write this. d power x by dx is equal to dy by dx. And we know from the previous slide that dy by dx is 1 over dx by dy. So now can we replace dx by dy with its value in this equation, 1 over e power x? Yes. So we'll have 1 over 1 over e power x. So now we will have e power x up in the numerator, so the answer is equal to e power x. Thus, we reach that the derivative of e power x with respect to x is equal to e power x. In general, whenever we have a differentiable function u of x, we can say that the derivative of e power u of x with respect to x is the e power u of x multiplied by the derivative of u of x. So the derivative of e power u of x with respect to x is e power u of x multiplied by the derivative of what's in the exponent. Let's write it with the inside word, d of e power inside with respect to dx is equal to e power inside multiplied by derivative of inside with respect to x. And we move on to examples. Let's see the following examples in the current slide. Differentiate y equals e power x squared plus 3x. We know that the derivative of the exponential function e power u of x or e power inside is e power inside multiplied by derivative of inside. So it's e power inside e power x squared plus 3x multiplied by the derivative of x squared plus 3x, which is 2x plus 3. We move on to the next example. We have y equals e power 2x multiplied by ln of x squared plus 1. So here we have the product of two functions, u and we will apply the product rule, which is y prime is equal to u prime v plus u v prime. We will take u to be e power 2x and v to be ln of x squared plus 1. Now, what's u prime? It's e power 2x multiplied by the derivative of the exponent, which is 2. And then what's v prime? V prime is the derivative of a logarithmic function. It will be 1 over inside multiplied by the derivative of inside. What's the derivative of inside? It's 2x. So we will have v prime to be 2x over x squared plus 1. We take everything here and we go to the product rule and we plug in u, u prime, v, and v prime. Okay? So we will get, for the first term, u prime is 2 e power 2x, v is ln of x squared plus 1, plus u, which is e power 2x, multiplied by v prime, which is 2x over x squared plus 1. Now let's take the 2 multiplied by the e power 2x common factor. We can see it here and also here. So this will give us 2 e power 2x multiplied by ln of x squared plus 1 plus x over x squared plus 1. And that's it for this example. In the present slide, we are going to present how can we differentiate y equals to b power u of x, any constant raised to the power of u of x. So we will write first that b is equal to e power ln b, and we all know that e and ln are a function and its inverse. So here we have b power u is equal to e power ln b power u. Again, we are applying the same property, e and ln. They are a function and its inverse. So we go here and take the u down. Here we apply the property of logarithms. So we have e power u multiplied by ln b. Next, we differentiate both sides with respect to x. So here we have d by dx of the left-hand side is equal to d by dx of the right-hand side. And on the right-hand side, we have an exponential function. And we all know how to differentiate an exponential function. So we have e power u ln b multiplied by the derivative of the exponent, and the derivative of the exponent is the constant ln b multiplied by the derivative of u of x with respect to x. So in this step, we keep the ln b as it is, the du by dx as it is, and we take the e power u ln b and we put it back to its original form. We have it up here. So here we arrive at the formula we want. Now let's see an example. Differentiate y equals 5 raised to the power of x squared plus 3x. Okay, we will apply the same rule. So this will be equal to y prime equals ln the base, ln 5, multiplied by the function itself, 5 power x squared plus 3x, multiplied by the derivative of what's in the exponent, which is equal to 2x plus 3. And that's it. Now let's see another example. Y equals e power 3x plus x power pi plus e power pi plus pi power x squared. We all know the pi, okay? So this is a constant. So now let's see how will we differentiate term by term. The first term will be differentiated to be the exponential function times the derivative of the exponent, which is 3. So here we have, for the first term in differentiation, we have 3 e power 3x plus x power n. We know how to differentiate x power n, so this will be equal to, we put the n down, pi, and we reduce the exponent by 1, so we have pi x power pi minus x minus 1. And then we come to this term. This term actually is a constant, so its derivative is 0. And finally, we come to the pi x squared. Again, we apply this formula. So we have the same function, pi x power x squared, multiplied by the derivative of the exponent, which is 2x, multiplied by the logarithm, or ln, the natural logarithm of the base, which is ln pi. Now, let's see the next. Here we have an example. Differentiate y equals x power n over n power x, where n is greater than 0. Okay, here we have u over v. So we need to apply the quotient rule. We will take the u to be x power n and the v to be the denominator, n power x, and then we will find the corresponding u prime and v prime. Here we have u prime is n into x power n minus 1. Here we'll have v prime to be ln the base, ln n, multiplied by n power x itself, multiplied by the derivative of the exponent, which is 1 in our case. Now we apply the quotient rule. Denominator squared, denominator times derivative of numerator minus numerator times derivative of denominator. We write again, one more time. We're just showing you how you will have the quotient rule applied. Now we plug in the u prime, the v prime, and we take a common factor. So we have n power x taken as common factor, and we cancel it with one of the n power x in the denominator. So we will get x power n minus 1 multiplied by bracket. Inside it we have n minus x ln of n over n power. Here we come to an application of derivative of exponential functions. We are given the charge of a capacitor in a circuit containing a capacitor of capacitance C, resistance R, and source of voltage is E. We have Q, the charge is equal to CE multiplied by 1 minus E power minus T over RC. We are asked to prove that this form of the charge is satisfying the differential equation R multiplied by dq by dt plus q over c is equal to E. It's very straightforward. We will first evaluate dq by dt, and then we will take the left hand side, plug in the derivative dq by dt, and plug in the q, which is given in front of us by this equation, equation 1, and we call this equation 2, and we will proceed to solve. So first step, we will differentiate both sides of equation 1 with respect to t. So here we will have dq by dt is equal to, here we have CE times 1, this is constant, so the derivative is 0, and then we differentiate minus e power minus t over RC. Again, we have an exponential function. The derivative will be the same exponential function times the derivative of what's in the exponent. What's in the exponent? The derivative is minus 1 over RC, and we have a minus sign. Minus times minus will be positive. So here we will have CE, the constant, we have it as it is, 1 over RC, which was minus, and then we multiplied it by minus, so we have positive 1 over RC multiplied by the exponential function itself. And we all see that we have C here and C here, so we can cancel them. Next, we rewrite it after cancellation, and we call this equation number 3. From 3 and 1, as I said, we will substitute into the left-hand side of this equation number 2 so that we can find the value of the sum of these two terms. Okay, so we will make a substitution for dq by dt here, and we will make a substitution from equation 1 for q, and we see what we get. So this is r dq by dt plus q over c. This is the left-hand side. So here is the r, and we are substituting the derivative, which is given by equation number 3. Yes. Plus q over c, we put a fraction line, and then in the numerator we put the q, which is given by equation 1, divided by c. And also we see that we can cancel here c with c and r with r. So making the cancellations, we get this for the first term, e into exponential function power minus t over rc. And for the second term, we get e multiplied by 1 minus exponential function e power minus t over rc. Can we see that there is e here and e here, which can be taken as common factor? Yes. So we take e as a common factor, and we are left with these three terms, two of which will add up to 0. Yes. So these add up to 0, so we are left with E, which proves what we are looking for in equation number 2. So we tried to reach from left-hand side to right-hand side, and we did this in this final step.